Let's look at 12.142 in the 13th edition. Okay, so a toboggan is traveling down along a curve. Let me just bring this a bit closer. Okay, so a toboggan, basically like a sled, is traveling down this curved path, and the curved path is given by y equals 0.01 x squared. Okay, and at point A, the horizontal distance is 60, the vertical distance is 36. It says, determine the magnitude of its acceleration when it reaches point A, where its speed is 10, VA equals 10 meters per second, and it is increasing at a rate of VA dot equal to 3 meters per second squared. Okay? So here's 12.142. This is in the 13th. And we've got this, and we've got this curve here. That's point A. And what else do we know? 60 meters here. Right, so this is my X, that's the Y, and this will be 36 meters. And this curve is given by a Y equals 0.01 x squared. So the question is, we want the acceleration. What is the acceleration, the magnitude of its acceleration when it reaches point A? Okay, where are we going? Where are we going? This is where we're going. Acceleration is AT UT plus V squared over rho UN. We want this so that we can calculate the magnitude, which is AT squared plus V squared over rho squared. Okay, that's where we're going. We want, this is if we're using normal and tangential components. So what do? There's our normal direction, and there's our positive normal and our positive tangential. Okay, because we know the particle is going in this direction, the sled is going down, so there's our positive T, there's our positive N. All right, so where we're going, like I said, that's what we want. So we want these components. What do we have? We have at A, our velocity is 10 meters per second, and that's VA. Then they say VA dot is what? 3 meters per second squared. What is VA dot? Please try to answer that for yourself. What is VA dot? That is simply AT, right? Simply that there. It is the change in velocity. Okay, so we've got this component. Do we have this component V? Yes, we've got it here. What about rho? Do we have rho? No, we do not have rho. What is rho? Please try to answer that. What is rho? Rho is your radius of curvature. Okay, so if we just bring this back here, at that point A, if you fit a circle with where the circle, a part of the circle forms the arc there, okay, remember the radius of curvature is the center of that circle. And the radius of curvature is where this, from point A to the radius of curvature is our normal direction, okay? So how do we calculate? Okay, so let's just recap. We've got AT, yes. We've got V, yes. Rho, recall rho is given by this. If we've got our curve in this form, 0.01 x squared, if we've got it in this kind of form, then recall that our radius of curvature, just based on calculus, is given by 1 plus dy dx squared, and this whole thing to the power of 3 over 2, divided by d2y dx squared, which is just your second derivative. So the first derivative of that, second derivative of that. If we plug that in, what is the first derivative? What's dy dx? It'll be 0.02x. What's d2y dx squared? 0.02. So we put that in there, we get 1 plus 0.02x. That thing must be squared. And that whole top must be to the power of 3 over 2 divided by 0.02, right? Okay, and then we know that it's at 60 meters in the horizontal. So we need to put 60 meters in there, and we will get a rho which is equal to, let me see, it was, if you put that in there, 60 times 0.02 squared is 1 to the power of 1.5 divided by 0.02, we will get 190.57 meters. Okay, that is your radius of curvature. That's your radius of curvature. Okay, so now if we take that again, A is equal to, or the magnitude of A, magnitude of the acceleration is given by AT squared plus V squared over rho, all squared, and the square root of that. We know that AT was given by 3, and we know that V was 10 squared. Now we've calculated rho, which is 190.57. Remember, this whole thing must be squared. Don't make that mistake because you see V squared, then you think, oh, I've already squared this component. No, V squared over rho is the component. You still have to square that entire component, right? And then we square root that, and we should get, so 10 squared divided by 190.57 equals, and we square that, plus 3 squared, and we take the root, and we get the magnitude of the acceleration is 3.045, basically 3.05 meters per second squared. Okay, that's the magnitude of the acceleration. Okay, now, like I always ask in class, if you've got the curve here and there's point A, let's draw the vectors. We know that this is my tangential component is 3, and this will be my normal component. There's my normal direction. There's my tangential direction. What is my normal? My normal will be 10 squared over this. So 10 squared divided by 190.57. So I've got an acceleration here of 0.525, essentially, meters per second squared. Right? That's this normal component, guys, the normal component. What about the tangential component? Well, it's given to us as 3 meters per second squared. And that's the acceleration there. 3 meters per second squared. And then, okay, it's not super accurate because this length must actually be 6 times this length approximately. So there's our acceleration, okay, which is 3.05. So please practice drawing these vector diagrams. You never know when you might see them. That just might happen in a test or an exam. Cheers.